Imagine standing at the edge of something impossible. In front of you, space itself has been torn open, folded in ways your brain was never designed to understand. Light bends around this cosmic wound, creating a sphere that shows you stars from the other side of the universe. You take a breath. You step forward. And in that moment, everything you thought you knew about time, about reality, about your own existence, begins to dissolve like morning fog under an impossible sun. What if I told you that the moment you cross that threshold, you might experience something that no human language has words for? What if the very concept of before and after stops making sense? What if your past, your present, and your future all collapse into a single, eternal moment that stretches across infinity and compresses into nothing, all at once? This is not science fiction. This is what the mathematics of our universe actually predicts. This is what happens to time inside a wormhole. But before we take that journey together, before we step into the cosmic unknown, I need you to do something. I need you to prepare your mind for what we're about to explore. Hit that subscribe button, because this channel is dedicated to exactly these kinds of mind-expanding journeys through the cosmos. Smash that like button, because it helps other curious minds find this content. And drop a comment right now telling me this. If you could travel through a wormhole to any point in time or any location in space, where would you go? What moment in history would you witness? What distant world would you explore? I will be reading your answers, and I genuinely want to know what cosmic destination calls to your soul. Now, let us begin our journey. But to understand what happens to time inside a wormhole, we first need to understand something far more fundamental. We need to understand what time actually is, and I promise you, the answer is nothing like what you think. Close your eyes for a moment and think about time. What do you see? Most people imagine a river, flowing steadily from the past toward the future, carrying us along whether we want to go or not. We wake up, we live our day, we go to sleep, and time has moved forward. It feels so natural, so obvious, so clearly true. But here is the first twist in our journey. Everything you just imagined is an illusion created by your brain. Your brain evolved over millions of years to help you survive on the African savanna. It needed to predict when the sun would rise, when predators might hunt, when fruits would ripen. So it constructed an experience of time that felt linear, that felt like flowing water, because that mental model helped your ancestors survive. But the universe, the actual physical reality we inhabit, does not care about your brain's survival mechanisms. The universe operates according to rules that are far stranger, far more beautiful, and far more terrifying than anything evolution prepared us for. Let us go back to the year 1687. Isaac Newton publishes his masterwork, the Principia Mathematica. In it, he describes a universe that operates like a perfect clockwork machine. Time, according to Newton, flows absolutely and uniformly throughout the entire cosmos. Every clock in the universe ticks at the same rate. Every moment of time is experienced identically, whether you're standing on Earth or floating near a distant star. This was the common sense view of time, the intuitive understanding that matched human experience. And for over 200 years, it worked perfectly. Engineers built bridges, astronomers predicted eclipses, and the Industrial Revolution transformed human civilization, all using Newtonian physics. But Newton was wrong. Not wrong in the sense that his equations did not work for everyday purposes. They did, and they still do. Wrong in the sense that he had described a simplified approximation of a far deeper reality. And it took a patent clerk in Switzerland to show us just how wrong our intuitions about time really were. In 1905, Albert Einstein was 26 years old, working at the Swiss Patent Office, reviewing applications for inventions, but in his spare time he was thinking about light, about motion, about time itself. And in that miraculous year, he published a paper that would shatter our understanding of reality. He called it On the Electrodynamics of Moving Bodies. Today we call it special relativity. Einstein asked a simple question that everyone else had ignored. What if the speed of light is always constant? Not just approximately constant, not just mostly constant, but absolutely, fundamentally unbreakably constant for every observer in the universe, regardless of how they are moving? This seems like a technical detail, but follow the logic and watch what happens to time itself. Imagine you are standing on a train platform. A train zooms past you at half the speed of light. Inside the train, someone turns on a flashlight pointing toward the front of the train. Common sense says the light should travel at the speed of light plus half the speed of light, giving a total velocity of 1.5 times the speed of light. But this cannot be true if light speed is constant. The light must still travel at exactly the speed of light, no more, no less. How is this possible? There is only one way to make the mathematics work. Time itself must pass differently for you standing on the platform than it does for the person on the train. Clocks tick at different rates depending on how fast they are moving. This is not a metaphor. This is not a trick. This is physical reality. When you move faster through space, you move slower through time. This is time dilation, and it has been measured with atomic clocks on airplanes, with particles in accelerators, with satellites in orbit. Every single experiment confirms what Einstein predicted. Time is not a universal constant. Time is relative. Time is flexible. Time is personal. But Einstein was not finished. 10 years later, in 1915, he unveiled his masterpiece, General Relativity. This theory is so profound, so revolutionary, that many physicists consider it the most beautiful scientific achievement in human history. And it makes time even stranger than special relativity ever suggested. General relativity says this: mass and energy curve space-time. Gravity is not a force pulling objects toward each other. Gravity is the curvature of space-time itself. When you drop a ball, it does not fall because Earth is pulling it down. It falls because Earth's mass has curved the space-time around it, and the ball is simply following the straightest possible path through that curved geometry. The ball is actually traveling in a straight line, but the straight lines themselves are bent. And here is the crucial part for our journey. When space-time curves, time slows down. The stronger the gravitational field, the slower time passes. This is not theory, this is measured fact. GPS satellites must constantly adjust their clocks, because time literally passes faster for them, orbiting high above Earth where gravity is weaker than it does for us on the surface. Without these adjustments, your GPS would be off by kilometers within a day. Stand at sea level, and time passes at one rate. Climb a mountain, and time passes slightly faster. Fall toward a black hole, and time slows dramatically. At the event horizon of a black hole, from an outside observer's perspective, time essentially stops. An astronaut falling in would appear to freeze at the edge forever, their image redshifting into oblivion over billions of years. But from the astronaut's perspective, they would cross the horizon in an instant and fall toward the singularity. Do you see what this means? Time is not a river flowing uniformly for everyone. Time is a landscape with hills and valleys, moving differently in different places, and wormholes are the ultimate expression of this malleability. They are places where time does not just bend, it breaks. But what exactly is a wormhole? Where did this concept come from? And why do physicists take it seriously rather than dismissing it as fantasy? The year is 1935. Einstein, now world famous, is working at the Institute for Advanced Study in Princeton, New Jersey. Together with his colleague Nathan Rosen, he's exploring the mathematics of black holes, trying to understand these bizarre objects predicted by his own equations, and they discover something unexpected. When you write out the full solution for a black hole's space-time geometry, there is a hidden structure. The mathematics suggests that the singularity at the center of a black hole might connect to another singularity somewhere else. Two black holes, potentially in completely different regions of space, or even in completely different universes, joined at their centers through a tunnel in space-time. And Einstein and Rosen called this a bridge. Today we call it an Einstein-Rosen bridge, or more commonly a wormhole. The term wormhole was coined later by physicist John Wheeler, the same brilliant mind who gave us the term black hole. Wheeler imagined a worm eating through an apple, taking a shortcut from one side to the other instead of traveling along the surface. A wormhole does the same thing to space-time. Here is how to visualize it. Imagine the universe as a flat sheet of paper, representing two-dimensional beings who can only move along the surface. 2 points on this paper might be very far apart if you travel along the surface. But what if you fold the paper so those 2 points touch? And then what if you punch a hole connecting them? Suddenly, what was a vast distance becomes a single step. A wormhole does this in 4 dimensions. It folds space-time so that two regions that might be billions of light years apart, or billions of years apart in time, become directly connected through a shortcut. The throat of the wormhole, the narrowest part of the tunnel, might be just a few kilometers wide, but the two mouths, the openings at either end, could open onto completely different parts of the cosmos. Now, Einstein himself did not believe wormholes were physically real. The original Einstein-Rosen bridge had a fatal flaw. It would pinch off instantly, faster than even light could travel through. Anything trying to traverse it would be crushed by the collapsing geometry. It was mathematically interesting but physically useless. For decades, wormholes remained a curiosity, a mathematical oddity that nobody took seriously as a real phenomenon. But then something remarkable happened. A phone call changed everything. In 1985, Carl Sagan was writing his novel Contact, about humanity's first message from an alien civilization. He needed a scientifically plausible way for his protagonist to travel across the galaxy. He called his friend Kip Thorne, one of the world's leading experts on general relativity, and asked, "Is there any way to travel faster than light without violating physics?" Thorne took the question seriously. He and his students began working on the mathematics, looking for a loophole in Einstein's equations, and they found one. In 1988, Thorne and his colleagues published a paper that would revolutionize the field. Wormholes, time machines, mold, and the weak energy condition. The key insight was this. The original Einstein-Rosen bridge collapsed because it was made of normal matter and energy. Normal matter creates attractive gravity, which pulls the throat closed. But what if you could fill the wormhole with something different? What if there existed a type of matter with negative energy density, matter that creates repulsive gravity, pushing the throat open instead of pulling it closed? This exotic matter would thread through the wormhole like scaffolding, holding it open against the natural tendency to collapse. A traversable wormhole, one you could actually travel through and survive, became theoretically possible. Not easy, not practical with current technology, but permitted by the laws of physics. And here is the really strange part. Exotic matter might actually exist. Quantum mechanics, that other pillar of modern physics, predicts that empty space is not truly empty. It seethes with virtual particles popping in and out of existence, borrowing energy from the vacuum for brief moments. Under certain conditions, particularly in the Casimir effect, this quantum activity can create regions with negative energy density. The same exotic matter that wormholes need. The Casimir effect has been measured in laboratories. Two metal plates placed very close together experience a tiny attractive force because there are fewer virtual particles between them than outside. This is not speculation. It is experimental fact. Exotic matter is real, at least in microscopic quantities. Could we ever gather enough exotic matter to build a wormhole? With current technology, absolutely not. The energy requirements are astronomical, perhaps requiring the entire mass-energy output of a star concentrated into a tiny region. But technologically impossible today is very different from physically impossible forever. A medieval peasant would have considered a smartphone physically impossible. We have only been doing modern physics for about a century. Who knows what a civilization a million years more advanced might accomplish? But let us stop worrying about whether we can build one and start asking the question that brought us here. What happens to time inside a wormhole? This is where our journey becomes truly strange. This is where human intuition fails completely. This is where we must trust the mathematics even when it tells us things that seem impossible. Let me take you through the experience step by step, years moment by moment, or whatever remains of moments when time itself becomes uncertain. You are approaching a wormhole. Let us say this one has been stabilized by an advanced civilization, held open by exotic matter, safe for travel. The mouth of the wormhole looks something like a sphere, but not a normal sphere. Through it, you can see stars that should be on the other side of the galaxy. Light is bending around the edges, creating a thin bright ring that physicists call an Einstein ring. The view through the mouth is distorted, compressed, fish-eyed. You're looking through a lens made of curved spacetime itself. As you get closer, something begins to happen. Not to what you see, but to time itself. Remember, mass and energy curve spacetime, and that curvature affects how fast time passes. The exotic matter holding the wormhole open, the enormous energies concentrated in its structure, create a gravitational environment unlike anything found in normal space. If someone far away were watching you approach, they would see you begin to slow down. Not your spaceship, but you. Your movements would become sluggish. Your voice on the radio would deepen and stretch. Your clock would tick slower and slower from their perspective. This is gravitational time dilation in action, the same effect that happens near black holes, now becoming significant as you approach the wormhole's throat. But from your perspective, nothing seems different. You check your watch, and it ticks normally. You feel normal, think normally, experience time flowing at what seems like its usual rate. This is the strange democracy of relativity. Everyone experiences their own time as normal. Even as outside observers see dramatic differences. You reach the mouth of the wormhole, you take a breath, and you cross the threshold. And now things get truly weird. The interior of a wormhole is not like the interior of a tunnel on Earth. There are no walls in the conventional sense. Instead, you are moving through a region where space-time itself has been twisted into an extraordinary geometry. The mathematics describing this region is complex, involving metrics and tensors and coordinate systems that physicists argue about intensely. But we can describe the experience, or at least our best theoretical models of what the experience might be. One possibility, perhaps the most mind-bending of all, is that time inside the wormhole's throat essentially stops. Not slows down, stops. The curvature of space-time becomes so extreme that the very concept of before and after loses meaning. You would exist in a state of pure, frozen now, an eternal instant. No past receding behind you, no future approaching ahead of you, just an infinite present stretched across what should be a finite journey. What would this feel like? This is a question that physics alone cannot answer, because physics describes the external world, not the internal experience of consciousness. But let us try to imagine it anyway. Have you ever had a moment of perfect stillness? Perhaps watching a sunset, perhaps holding someone you love, perhaps in meditation or prayer. A moment where the churning of thoughts quieted and you simply existed, present and aware, without the constant mental commentary of past regrets and future anxieties. Multiply that by infinity. Deepen it beyond anything meditation could achieve. That might be the closest approximation to experiencing frozen time inside a wormhole. Or perhaps it would be nothing like that. Perhaps consciousness requires time to exist at all. Perhaps thoughts cannot occur in a region where time has stopped. You would enter the wormhole and emerge instantly from your own perspective, with no memory of the transit, because memories require time to form. The wormhole would be an experiential gap, a discontinuity in your timeline, a skip from one moment to another with nothing in between. But here is where it gets even stranger. This is not the only possibility. Some theoretical models suggest something different happens inside a wormhole. Not that time stops, but that time becomes space. Let me explain what this means, because it is one of the most profound and disturbing ideas in all of physics. In normal space-time, we can move freely in 3 spatial dimensions. You can walk forward and backward, left and right, up and down, but you cannot move freely in time. You're stuck moving forward at a rate of 1 second per second, inexorably, inescapably. Time is different from space in this crucial way. Space allows freedom. Time is a prison. Inside a black hole, this changes. The mathematics of general relativity predicts that once you cross the event horizon, space and time exchange their properties. The direction toward the singularity, which was previously a spatial direction, becomes the new time direction. You can no more avoid the singularity than you can avoid tomorrow. Meanwhile, what was previously time becomes something you can move freely in. The past and future become directions you can travel just as easily as walking across a room. This might happen inside certain wormholes too. The interior region might be a place where the rigid arrow of time loosens its grip, where your future becomes negotiable, where your past is not locked away behind an impenetrable wall, but sits beside you like a door you could open. Think about what this would mean. Imagine standing in a hallway where yesterday and tomorrow are rooms you can enter at will. You could visit your own past, not as a memory, but as a place. You could scout your own future, not as a prediction, but as a destination you choose to enter or avoid. The linear narrative of your life, the story that flows from birth to death, would dissolve into something more like a landscape, a territory you could explore rather than a path you must walk. This is not metaphor. This is what the mathematics actually suggests might happen. General relativity permits solutions where time loses its time-like character, where the distinction between past and future becomes as arbitrary as the distinction between left and right. But wait, there is another possibility, perhaps the strangest of all. Some physicists believe that inside a wormhole, you might experience all of time at once. Not frozen time, not negotiable time, but simultaneous time. Every moment of your life from birth to death, experienced in a single instant of infinite duration. This connects to a philosophical interpretation of general relativity called eternalism, or the block universe theory. According to this view, all of time already exists. The past has not disappeared, the future has not yet to happen. Instead, the entire timeline of the universe, from Big Bang to whatever end awaits, exists as a complete, unchanging four-dimensional structure. We call it a block because it sits there, solid and eternal, containing every moment that ever was or will be. Our experience of time flowing, of the present moment moving through this block, is an illusion created by our consciousness. In reality, every version of you that ever existed still exists. The 5-year-old you, the you reading these words right now, the future you on your deathbed, they are all equally real, equally present, separated only by their position in the block. If this view is correct, and many physicists take it seriously, then perhaps a wormhole allows you to perceive the true nature of reality. Perhaps inside that twisted geometry, the illusion of flowing time breaks down, and you see the block universe for what it is. You experience every moment of existence simultaneously. You are born, and you die in the same eternal instant. You see the entire sweep of cosmic history, from the first particles emerging from the Big Bang to the last star flickering out in the cold darkness of heat death. What would this be like? Mystics have described similar experiences. Enlightenment traditions speak of perceiving all of time at once, of seeing through the illusion of temporal separation. Perhaps these were glimpses through meditation or extreme experiences of the same reality that a wormhole would reveal fully. Or perhaps these are just stories, and the true experience would be utterly alien to anything human consciousness can process. But let us explore one more possibility before we continue our journey. What if time inside a wormhole does not just stop or become negotiable or reveal its true nature? What if time reverses? Some theoretical solutions for wormholes include regions where time runs backward, not slowly, not frozen, but actively reversed. Effects precede causes. You remember the future and anticipate the past. Eggs unscramble, candles unburn, the dead rise and grow younger. This sounds like madness, like the universe playing a joke on physics. But the equations permit it. Imagine falling through such a region. You would experience the most profound disorientation possible. Your thoughts would run backward. You would unthink your memories, experience them in reverse, feel the future becoming the past and the past becoming the future. Your consciousness, which is fundamentally structured around the arrow of time, would confront a reality that contradicts its very foundation. Would you even survive this experience intact? Would there be a you on the other side, or would the person who emerges be somehow fundamentally different, their mind restructured by the reversal of causality? These questions touch on the deepest mysteries of consciousness and identity, questions that physics alone cannot answer. Let us take a breath here. We have been exploring the theoretical possibilities of what happens to time inside a wormhole, and we have encountered multiple scenarios, each stranger than the last. Time might stop. Time might become negotiable. Time might reveal its true nature. Time might reverse. But these are all models, theories, mathematical possibilities. What do physicists actually think is most likely? The honest answer is that nobody knows. Wormholes, if they exist at all, exist in a regime where our two great theories of physics, general relativity and quantum mechanics, both apply simultaneously and have not yet been unified. We do not have a complete theory of quantum gravity. We cannot definitively predict what happens inside a wormhole because our physics is incomplete at exactly the scales where wormholes become important. This is not a failure of science. This is the frontier of science. The most exciting place to be is at the edge of knowledge, where the map says, "Here be dragons," and in the case of wormholes and time, the dragons are very strange indeed. But let us continue our journey. You have entered the wormhole, experienced whatever temporal strangeness awaits in its interior, and now you are approaching the exit. What happens when you emerge? The answer depends critically on how the wormhole was constructed and where its two mouths lead. And this is where wormholes transform from merely being cosmic shortcuts into something even more extraordinary. This is where wormholes become time machines. Here is how it works. Imagine an advanced civilization creates a wormhole with both mouths initially in the same location. The two openings sit side by side, each leading to the other through the shortcut of twisted spacetime. Now they take one mouth and accelerate it to near the speed of light, send it on a journey to a distant star and back while the other mouth remains at home. Remember time dilation. The traveling mouth experiences less time than the stationary mouth. If the journey takes 10 years from the perspective of the stationary mouth, perhaps only 1 year passes for the traveling mouth. When the traveling mouth returns, the two mouths are no longer synchronized. They are still connected through the same short tunnel, but one mouth is now in what the other mouth considers the future. Step through the mouth that stayed home, and you emerge from the mouth that traveled 1 year after you left from your perspective, but 9 years in your past from the perspective of someone who stayed at the stationary mouth. Step through the mouth that traveled, and you go in the opposite direction, emerging 9 years in your future relative to your starting point. You have a time machine. This is not science fiction. This is what the mathematics of general relativity actually predicts. Kip Thorne and his colleagues worked out these calculations carefully, checking for errors, looking for reasons why it could not work. They found none. According to our best understanding of physics, wormhole time travel is theoretically possible. But here is where things get complicated. If you can travel back in time, what happens to causality? What happens to the principle that causes must precede effects? What happens to logical consistency itself? Imagine this scenario. You enter the wormhole time machine, travel back to yesterday, and convince yourself not to enter the wormhole. Now, if yesterday you does not enter the wormhole, then future you never traveled back, which means yesterday you was never convinced, which means yesterday you did enter the wormhole, which means future you did travel back. Do you see the problem? Logic itself breaks down. This is the grandfather paradox, perhaps the most famous time travel paradox, named after the scenario where you travel back and prevent your own grandfather from meeting your grandmother. How does the universe resolve this? Physicists have proposed several possibilities, each fascinating in its implications. The first possibility is self-consistency. This is called the Novikov self-consistency principle, after physicist Igor Novikov. It says that any time travel that occurs must be self-consistent. You cannot change the past because the past already includes any time travel that will ever happen. If you go back to convince yesterday you not to enter the wormhole, you will fail. Something will prevent you. Perhaps you will be distracted. Perhaps yesterday you will not believe you. Perhaps you will arrive at the wrong moment. Whatever happens, the result will be consistent with what actually occurred. This sounds like fate, like destiny, like the universe conspiring to prevent paradoxes. And perhaps it is. Perhaps the laws of physics constrain not just what is possible, but what can happen given the requirement of logical consistency. Every time travel loop is closed, every effect has its cause, and no paradoxes can occur because the paradoxes cannot occur. The second possibility is branching timelines. This is the many-world solution, drawing on the quantum mechanical interpretation where every possibility creates its own branch of reality. When you travel back and try to change the past, you succeed, but you succeed in creating a new timeline, a separate branch of the multiverse where things go differently. The original timeline continues unchanged. You have not changed your past, you have created a new version of it. In this view, the grandfather paradox resolves itself because you never actually interact with your own past. You interact with a different timeline's version of events. Your grandfather in that timeline might never meet your grandmother, but your original grandfather, in your original timeline, is unaffected. You can never return to your exact starting point, because that timeline continues forward without you. The third possibility is chronology protection. This is Stephen Hawking's proposal, his famous chronology protection conjecture. Hawking suggested that the laws of physics might include an as-yet unknown mechanism that prevents time machines from being created in the first place. Whenever a situation develops that would allow travel to the past, something intervenes to prevent it. What would this mechanism be? Hawking thought it might involve quantum effects. When a wormhole becomes a time machine, the moment of creation is called the chronology horizon. At this point, Virtual particles in the quantum vacuum can loop back on themselves through the wormhole, re-encountering their own past, creating an infinite cascade of energy. This energy would destroy the wormhole just as it becomes a time machine. The universe protects itself against paradoxes through self-destruction. Hawking called this the chronology protection agency, joking that there seemed to be a kind of cosmic enforcement mechanism keeping the past safe from interference. We do not know if he was right, but it is a tantalizing possibility. Perhaps time travel is forbidden not by current technology, but by the fundamental structure of the universe itself. But wait. Even if we cannot travel to the past, what about traveling to the future? This raises no paradoxes at all. You cannot change something that has not happened yet. And future time travel is not just theoretically possible, it is experimentally confirmed. Every time you move, you travel to the future slightly faster than you would standing still. Every time you experience stronger gravity, you travel to the future slightly slower. These effects are tiny at human scales, but they are real and measurable. Astronauts who spend time on the International Space Station return to Earth having aged a fraction of a second less than people who stayed on the surface. They have traveled to the future, just not very far. With a wormhole, the effect could be dramatic. Enter one mouth, exit the other mouth years or centuries in the future. You would see the world your descendants live in, experience technology and culture you cannot imagine, witness history yet to be written. There would be no paradoxes, no logical contradictions, just the bittersweet experience of leaving your own time behind forever. This is perhaps the most realistic application of wormhole physics. Even if the universe prevents backward time travel, forward time travel might be entirely permitted. And even if wormholes are forever beyond our technological reach, the principle remains. Time is flexible, time is personal, and with the right conditions, vast leaps into the future are possible. Let us pause our journey through the wormhole for a moment and consider something even more profound. We have been talking about time as if we understand what it really is. But do we? What is time at its deepest level? Here is a mystery that keeps physicists awake at night. In the fundamental equations of physics, there is nothing that says time must flow forward. The laws of motion work just as well run backward as forward. Drop a ball and watch it fall, then play the film in reverse and watch it rise. Both are equally valid solutions to Newton's equations. The same is true for almost every fundamental law we know. So why does time have a direction? Why do we remember the past but not the future? Why does entropy increase? Why do eggs break but not unbreak? Why do we age and die rather than growing younger? The answer seems to lie in something called the second law of thermodynamics. In any closed system, entropy, which you can think of as disorder or randomness, tends to increase over time. Hot things cool down, orderly structures decay, information disperses. This creates an arrow of time, a direction that distinguishes past from future. But here is the puzzle. The second law is not really a law, in the same sense as Newton's laws or Einstein's equations. It is a statistical tendency, a description of what usually happens given certain initial conditions, and it requires those initial conditions to be special. Specifically, it requires the universe to have started in a state of extremely low entropy, extremely high order, which has been increasing ever since. Why did the universe start that way? This is called the past hypothesis, and it is one of the deepest unsolved problems in physics. We do not know why the Big Bang produced a low-entropy universe. We just observe that it did, and from that observation, the arrow of time follows. What does this have to do with wormholes? Perhaps everything. If time's arrow comes from initial conditions rather than fundamental laws, then perhaps there are regions where local conditions create different arrows. Perhaps inside a wormhole, the relationship between entropy and time changes. Perhaps the arrow of time can bend or reverse or disappear entirely. Some physicists speculate that if you could travel through a wormhole to the far future of the universe, when entropy has maximized and the cosmos has reached heat death, the arrow of time might behave differently there. The past and future might become equivalent when there is nothing left to distinguish them. The eternal frozen darkness at the end of time might be timeless in a profound sense. And now, let us consider something even stranger. What if time is not fundamental at all? What if time is an illusion, not in the psychological sense we discussed earlier, but in the physical sense? What if time does not exist at the deepest level of reality, but emerges from something more fundamental? This is not wild speculation. It is a leading approach to solving one of the biggest problems in physics, the conflict between general relativity and quantum mechanics. These two theories are both extraordinarily successful in their domains, but they contradict each other when combined. General relativity describes gravity as the curvature of space-time, but quantum mechanics requires a fixed background of space and time against which to define its equations. The two frameworks are fundamentally incompatible. One approach to resolving this conflict is to say that space-time, including time, is not fundamental. Instead, space-time emerges from more basic quantum processes, much as the smooth surface of water emerges from the chaotic motion of trillions of molecules. At the deepest level, there might be no time, no space, just abstract quantum information following rules that have no intrinsic temporal structure. This idea is embodied in the Wheeler-DeWitt equation, a proposed equation for quantum gravity that describes the entire universe, but contains no time variable at all. In this framework, time is not woven into the fabric of reality. Time is a feature that appears only at larger scales, an approximation that works for everyday physics, but breaks down at the Planck scale, the incredibly tiny distances where quantum gravity becomes important. Wormholes might be windows into this timeless realm. The interior of a wormhole, with its extreme curvature and quantum effects, might be a place where the emergent nature of time becomes apparent. Perhaps the strange temporal phenomena we discussed, the stopping and reversing and simultaneous experiencing of time, are all manifestations of a deeper reality where time does not exist in any conventional sense. If you traveled through a wormhole to this timeless realm, what would you experience? Perhaps nothing, because experience requires time. Perhaps everything, because without time, all experiences exist at once. Perhaps something entirely beyond human comprehension, because our minds evolved to navigate a world where time exists and flows, and can be relied upon. We are reaching the edge of what physics can tell us and entering the territory of philosophy. But that is appropriate, because the question of time has always been both a scientific and a philosophical question. What is the nature of reality? What is the nature of experience? What does it mean to exist? These are questions that have occupied human minds since consciousness first emerged, and they remain unanswered despite all our scientific progress. Let us return to our journey through the wormhole and consider what you might see. We have discussed what happens to time, but what about space? What does the interior of a wormhole look like? The best visualizations we have come from computer simulations using Einstein's equations. The view is surreal, disturbing, beautiful. As you approach the mouth, you see the distant stars through a circular window, distorted and warped by gravitational lensing. The edges of the mouth are ringed with light, an Einstein ring where photons from all directions are bent to meet your eye. Through the mouth, you see a different sky, the sky of wherever the other mouth opens, superimposed on your current view. As you enter, the view shifts dramatically. The mouth behind you expands, showing more and more of the universe you left behind, even as the mouth ahead shows more and more of your destination. You're seeing through both ends of a tunnel that does not exist in normal space, viewing two skies at once, separated by vast distances but joined through twisted geometry. Inside the throat, the narrowest point, the distortion is extreme. Space is compressed in one direction and stretched in another. The universe outside appears to wrap around you like a glowing shell. You're at the pinch point of infinity, the place where space-time is most dramatically curved, and the view is impossible to describe in ordinary language because ordinary language evolved to describe ordinary space. And then you emerge. The sky shifts, the distortion reverses, and you find yourself somewhere else. Perhaps it is another galaxy, 2 million light-years from home. Perhaps it's the same galaxy, but 1 billion years in the past or future. Perhaps it is another universe entirely, governed by different physical constants, where the stars shine in colors you have never seen, and matter behaves in ways that violate everything you know. The journey is complete, but you are not the same person who entered. Whether time stopped or reversed or revealed its true nature, whether you experienced an eternal instant or all of history at once, the wormhole has changed you. You have glimpsed something that human beings were never meant to glimpse. You have touched the naked fabric of reality, felt the flexibility of time itself, experience the universe at its strangest. Now let us bring our journey back to Earth, hide back to the present moment, and consider what all of this means for us. Wormholes may or may not exist. Time machines may or may not be possible. The true nature of time remains mysterious. But the physics we have explored is real, verified, foundational to our understanding of the cosmos. Time dilation is real. The flexibility of space-time is real. The possibility of exotic matter is supported by quantum mechanics. The mathematics that permits wormholes is the same mathematics that describes black holes, gravitational waves, and the expansion of the universe. We are not discussing fairy tales. We are discussing the logical consequences of our best-tested scientific theories. And here is something remarkable. We are making progress. In 2022, scientists at Google and various universities used a quantum computer to simulate a simplified version of a wormhole. They created a quantum system that mimicked the mathematical structure of a wormhole's geometry and sent quantum information through it. This was not a real wormhole in space-time, but it was a meaningful step toward understanding how wormholes work and whether the theory holds together. This connects to one of the most exciting developments in theoretical physics in the past decade, the ER equals EPR conjecture. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a revolutionary idea. They suggested that Einstein-Rosen bridges, wormholes, are equivalent to Einstein-Podolsky-Rosen pairs, quantum entangled particles. What does this mean? Quantum entanglement is the phenomenon where two particles become correlated in such a way that measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance, and thought it proved quantum mechanics was incomplete. But entanglement has been confirmed by numerous experiments. It is real, even if it is strange. Maldacena and Susskind proposed that every pair of entangled particles is connected by a tiny wormhole. Entanglement is not spooky action at distance. Entanglement is a direct connection through space-time itself, a microscopic Einstein-Rosen bridge joining the particles together. If this is true, and many physicists take the idea seriously, then wormholes are not exotic and rare. Wormholes are everywhere, connecting entangled particles across the universe, forming a hidden network of space-time shortcuts that underlies quantum mechanics itself. The universe is threaded with wormholes, and we are only now beginning to understand what this means. This also suggests that space-time and quantum mechanics are not separate phenomena but two aspects of the same underlying reality. Entanglement creates space-time. The geometry of the universe emerges from quantum connections. The distance between 2 points depends on how they are entangled, and wormholes are just the most dramatic manifestation of this deeper truth. We are living in an extraordinary time for physics. The questions we have explored today about wormholes and time and the nature of reality are not settled. They're actively being investigated by some of the smartest people on Earth, using the most powerful tools ever created. New observations are planned, new theories are being developed, new experiments are being designed. We might learn the answers within our lifetimes, or we might not. Some questions remain unanswered for centuries. Some questions might be forever beyond human reach. But the journey of exploration, the process of asking and investigating and wondering, has value in itself. We are conscious beings in an unconscious universe, trying to understand our situation, trying to glimpse the truth behind the veil of appearances. That is a noble endeavor, perhaps the noblest endeavor, and it does not require answers to be meaningful. Let us now consider some of the philosophical implications of what we have discussed. If time can be manipulated, if past and future are not as absolute as they seem, what does this mean for how we should live? Key one perspective says that if the block universe is true, if all of time already exists, then free will is an illusion. Your future is already determined, already exists as part of the timeless block, and your sense of choosing is merely the subjective experience of time playing out along a predetermined path. You're not writing the story of your life, you're reading a story that has already been written. But another perspective says that even if the block universe is true, the fact that you experience choosing still matters. Your experience is real, even if it is incomplete. The view from inside time is different from the view from outside time, and both views are valid. Just because the future exists does not mean you do not create it. You're both the author and the character, the observer and the observed. There is also the possibility that the block universe is not the final word. Quantum mechanics introduces genuine randomness into the universe, events that cannot be predicted even in principle. Some interpretations suggest that the future is genuinely open, that multiple possibilities exist in superposition until observation collapses them into actuality. In this view, the block is being constructed as time progresses, not pre-existing, but coming into being moment by moment. If this is true, then wormholes to the future might show you only one of many possible futures. The timeline you visit would become actual by your observation, but other timelines with different outcomes might exist in parallel. The multiverse blooms with every quantum event. Agent and wormholes might connect not just different points in time, but different branches of reality itself. Consider what this means for identity. If you travel through a wormhole and meet your future self, which one is really you? The present you, experiencing the journey? The future you, with all the memories and experiences of years yet to come? Are you the same person across time, or is the you of each moment a different entity, linked by memory and causality but not truly identical? These are ancient philosophical questions given new urgency by modern physics. The same questions were asked by Buddhist philosophers thousands of years ago, by Enlightenment thinkers wrestling with personal identity, by contemporary cognitive scientists studying the nature of consciousness. Physics does not answer these questions definitively, but it provides new frameworks for considering them, new constraints on possible answers. Here is a thought experiment that might illuminate the puzzle. Imagine that wormhole technology becomes available, and people routinely travel through time. You meet your future self, have a conversation, learn things about your own future. Then your future self returns to their time, and you continue living your life, eventually becoming that future self who traveled back. But when you do, you find that your memories of the conversation do not match what your past self says happened. The paradox cannot arise if the Novikov Principle holds, so something has gone wrong. What? One possibility is that memory is not perfectly reliable across wormhole journeys. Perhaps the experience of traveling through distorted time disrupts neural processes, altering memories in subtle ways. You remember a conversation that did not quite happen, or forget details that were crucial. The paradoxes are avoided not through cosmic enforcement, but through the simple unreliability of human memory. Another possibility is that consciousness itself is affected by wormhole travel. Perhaps the you that emerges is not quite the you that entered, with altered brain states, different neural configurations, and a slightly different personality. The philosophical ship of Theseus, the question of whether a ship remains the same ship if all its parts are replaced, takes on new meaning when the replaced parts are neurons and memories. But let us step back from these deep waters and consider something more immediate. Even if we never build wormholes, even if time travel remains forever theoretical, what we have learned matters for how we understand our place in the universe. Time is not what common sense says it is. The past is not erased, the future is not non-existent, and the present moment, the now, that feels so real and immediate, may be a peculiar feature of conscious experience rather than a fundamental aspect of reality. We live in an eternal block, or an ever-branching tree or some other structure we have not yet imagined, and our experience of flowing time is just one perspective on that larger reality. This can be frightening. The solid ground of common sense is pulled away, leaving us floating in a conceptual void. But it can also be liberating. If time is not a river carrying us helplessly toward death, but a landscape we are always fully part of, then perhaps death itself is not what it seems. The you of this moment will always exist in the block, will always be reading these words, thinking these thoughts, experiencing this experience. Death is not an erasure but a boundary, like the edge of a country. The territory continues even where your journey ends. I want to tell you about a beautiful concept from physics that connects to this idea. It is called the principle of least action. In classical physics, objects do not just move randomly. They follow paths that minimize a quantity called the action, which is related to energy and time. Remarkably, they seem to know in advance where they are going, choosing the path of least action, as if they could see the future. Of course, particles do not really know anything. The principle of least action is equivalent to Newton's laws, just stated differently. But the formulation is suggestive. It hints at a universe where the future influences the present, where final states matter as much as initial states, where time is not fundamentally directional at all. Some speculative theories take this hint seriously. The transactional interpretation of quantum mechanics, proposed by physicist John Cramer, imagines that quantum events involve waves traveling both forward and backward in time. An interaction is not a cause followed by an effect, but a handshake between past and future, a transaction negotiated across temporal boundaries. If this interpretation is correct, the universe has always been doing what wormholes might enable us to do, connecting different moments in time, creating causal loops, weaving the fabric of time into complex non-linear patterns. These ideas are speculative. They might be wrong, but they illustrate the richness of possibilities that modern physics opens up. The universe is not required to match our intuitions. The universe is not required to be simple. The universe is whatever it is, and our job is to discover its nature, not to dictate it. Let us take a moment to reflect on the sheer improbability of our situation. We are conscious beings, made of atoms forged in ancient stars, living on a small rocky planet orbiting an ordinary yellow sun in a vast cosmos of hundreds of billions of galaxies. We have developed mathematics and physics and technology to the point where we can ask meaningful questions about the nature of time, about the possibility of wormholes, about the structure of reality itself. A few centuries ago, these questions could not even be formulated properly. A few millennia ago, the cosmos was a dome of lights above a flat Earth, populated by gods and monsters. A few million years ago, our ancestors were small animals hiding from predators, with no conception of time beyond immediate experience. And yet here we are, contemplating the block universe and quantum gravity and traversable wormholes. This is remarkable. This is worthy of awe and celebration. Whatever the ultimate answers turn out to be, the fact that we can ask the questions is a triumph of the human spirit, a testament to our insatiable curiosity and our stubborn refusal to accept mystery without investigation. And now, as we approach the end of our journey together, let me paint a picture of what the future might hold. Not the far future of heat death and maximum entropy, but the near future, the future that some of you might live to see. Imagine a century from now, quantum computers have become powerful enough to simulate complex physical systems with perfect accuracy. We run simulations of wormhole geometries, not simplified versions like the 2022 experiment, but full, detailed models that capture every nuance of general relativity and quantum mechanics together. We discover whether wormholes are stable, what kind of exotic matter they require, and whether chronology protection prevents time machines. Maybe we discover that wormholes are impossible after all. Some subtle quantum effect destroys them before they form, or the exotic matter requirements exceed any possible energy source, or the mathematics contains a hidden inconsistency we missed. We learn that the universe, at least in this respect, matches common sense after all. Time flows forward, the past is fixed, the future is open, and there are no shortcuts. Or maybe we discover that wormholes are possible. Maybe we find a way to create them, not with the energy of stars, but with some clever quantum trick we have not yet imagined. We build the first artificial wormhole, a microscopic tear in spacetime, barely large enough for a photon to pass through. We send signals faster than light, instantaneous communication across the galaxy, transforming civilization in ways we cannot predict. And then, eventually, we make them bigger, large enough for matter, large enough for humans. The first explorers step through, pioneers in the truest sense, journeying not just to new places but to new possibilities. Perhaps they travel to other galaxies, is exploring in person what we now see only through telescopes. Perhaps they travel to other times, witnessing the great events of history or scouting the distant future. Perhaps they travel to other universes, dimensions stacked beside our own, filled with wonders and dangers we cannot imagine. This is not guaranteed, it might be impossible, but it is not ruled out by current physics, and the history of science teaches humility about what is possible. Radio waves were once theoretical speculation. Atomic energy was once a fantasy. Space travel was once the stuff of dreams. Today's fantasy can become tomorrow's engineering if the laws of physics permit it. What would you do if you could travel through a wormhole? Where would you go? What would you want to see? The birth of the universe, that first moment of creation when time itself began. The death of the Earth, billions of years in the future, when the sun expands to engulf our planet, a world around a distant star where life evolved differently, producing forms we have never imagined. Another version of yourself in a branching timeline who made different choices and lived a different life. These are the questions I asked you at the beginning, and now I ask them again, with the full weight of everything we have explored behind them. Drop a comment and let me know. I genuinely want to hear your answers, to know what cosmic destinations call to your soul. But whatever your answer, I hope this journey has given you something valuable. A sense of the strangeness and beauty of the universe we inhabit, an appreciation for the power of physics to illuminate deep questions, a feeling of connection to the great human project of understanding, the ongoing effort to figure out what is really going on. Time is strange. Time is flexible. Time might be an illusion, or an emergent phenomenon, or a landscape we can travel through in ways we never imagined. Wormholes might be impossible fantasies, or they might be the key to the cosmos, waiting for us to unlock them. Either way, the questions are magnificent, the investigation is noble, and the journey is worth taking. We have travelled far together, from the basics of time and space through the twisted geometry of wormholes to the deepest questions of philosophy and existence. We have seen how Einstein's theories transformed our understanding, how the mathematics permits possibilities that boggle the mind, and how physicists today are still pushing the boundaries of knowledge. But I want to leave you with something more personal, something that does not require exotic matter or advanced civilizations or future technology, something you can experience right now in your own life without ever building a wormhole. Time dilation is real, and you experience it every day, not through velocity or gravity, but through consciousness. When you're bored, time crawls. When you're engrossed in something you love, time flies. When you face danger, time seems to slow, giving you extra moments to react. When you meditate deeply, time can seem to stop entirely, giving you a taste of that eternal present we discussed. Your experience of time is malleable, flexible, personal. You're not passive flotsam carried along by time's river. You're an active participant in how you experience your life, your moments, your existence. This is not physics. It is psychology, but it connects to the same deep truth. Time is not what common sense says it is. Time is mysterious, and that mystery is accessible to you right here, right now, without any technology at all. So here is my challenge to you. In the days and weeks to come, pay attention to your experience of time. Notice when it speeds up and when it slows down. Notice the eternal present that underlies all your experiences, the unchanging now that is always with you regardless of what clock time says. This is not wormhole physics, but it touches the same mystery, and it might be more valuable than any technological breakthrough, because it is available to every conscious being any time they choose to look. The universe is vast beyond comprehension. Time is strange beyond intuition. Reality is mysterious beyond imagination. And yet here you are, conscious, curious, seeking understanding. That is beautiful. That is precious. That is something to celebrate. Thank you for joining me on this journey. If you have made it this far, you are part of a rare group, the ones who are willing to spend hours exploring the deep questions, who are not satisfied with surface answers and easy explanations. I respect that. I appreciate that, and I hope to see you on future journeys, exploring other corners of this magnificent cosmos. Hit that subscribe button if you have not already. There is so much more to explore, so many more mysteries to investigate, so many more journeys to take. Like this video if it expanded your mind, and share it with someone who would appreciate having their mind expanded too. The more of us who think about these questions, the more likely we are to find the answers. And remember, no matter what physics ultimately tells us about wormholes and time machines and the block universe, you are here now. This moment is real. Your curiosity is real. Your wonder is real. And in a universe that might be timeless, that might contain every moment eternally, this particular moment, where you chose to spend your time learning and thinking and wondering, is one of the best moments you could have chosen. The journey through the wormhole is complete. But the journey of understanding is never complete. It continues as long as there are conscious beings asking questions, seeking truth, marveling at the strangeness and beauty of existence. What happens to time inside a wormhole? Perhaps time stops. Perhaps time becomes space. Perhaps all of time happens at once. Perhaps time reverses. Perhaps time reveals its true nature as an illusion. a construction, an emergent phenomenon arising from something deeper. We do not know for certain, we may never know for certain, but we keep asking, keep investigating, keep wondering, and that, in the end, is what makes us human. Until next time, stay curious, keep questioning, and never stop exploring the magnificent mystery of existence. The cosmos awaits. End.